Whether it's a multi-million dollar chemical industry having thousands of instruments or your renewable energy projects with green hydrogen, this amazing instrument will remain common regardless of your project, and that is simple orifice plate. This orifice plate has such a simple working that you put as a restriction in a flow, and there's a dp created across it, and this dp is proportional to flow. But trust me, there has been such amazing research done throughout the world in trying to find out the best practices for orifice. But you know what is the most important thing? In an orifice flow meter, whenever it has asked about standards, there people say there is only one standard for orifice, and that is ISO 5167. This is an absolutely incorrect understanding. There are so many important standards that have been available, like API, ISO, ASME, PIP, just to name a few. In this video, we will explore all of these amazing standards. So let's get started. The first standard being is ISO 5167, because this is the most famous of all. ISO 5167 is basically divided into four parts. Let us explore each part. So the part 1 basically deals with your general principles. Part 2 deals with orifice plates, which is most important to us right now. Part 3 deals with the nozzles, and part 4 deals with Venturi tube. So let's look into part 2 now. Now here's the index of part 2. So I would try to just summarize with an easy way of trying to divide the index into four important categories. The first category being the type of tappings which are defined in the standard. For example, when to go for corner tappings, flange tappings, D by do tappings, etc. The equations for sizing the orifice, installation, this is very important. Now we look into this, and then finally the flow conditioners to be used. Now let us look into this important aspect which is mostly used for ISO 5167, is the installation guidelines. So in an orifice plate, one important thing is that the flow should not have swirls in it, something like this. So you have to have certain upstream requirements and downstream straight run requirements, so that there is no swirl created in the flow. Now the point is, what if you have example 10D, 5D, and this is being used for a normal pipeline? But what if this has an elbow in it? Don't you think there will be more swirls created because of the elbow, and the same straight run, for example 10D, might not be sufficient? For such cases, we are having a table here which is called as table 3. This table 3 is without flow conditioners. The table 4 is having flow conditioners as well. Now the point is, how is to read the table? This table has a lot of values. So first thing to remember is, let us try to take a small example of the table. So here on the left hand side you are having beta ratio, and on the right hand side you will be having various conditions. For example, single bend elbow, double elbows, elbows in the same plane, different plane, gate valve is open, closed, etc. And in the beta ratio in the left section you will have all the various combinations like 0.2, 0.4, 0.6, 0.8, and so on. Now, in terms of the bending, you will have one thing, which is the table is divided into A and B category. A stands for when you want very strict measurements, so your zero additional uncertainty is what it guarantees. B is when you are having 0.5% additional uncertainty. This is depending on what is your fluid. For example, if it is water, you might not be that strict, right? So example for A table, if the straight run is requirement is 6, for B it is 3, so 3 diameters upstream is what is the requirement. Similarly would be there for the downstream in the table. Now here if you see for A, here you require 16 diameters upstream, but in the B table again 3 is okay for you. This is how you can read this table in ISO 5167. Now, similar to this is another amazing standard, which is API MPMS 14.3. I personally love this standard. Very similar to Orifice, this is also divided into four parts, but they are called as chapters. Chapter 1, 2, 3, 4. Let us try to dig into understanding what are these chapters. The first one stands for general equations. Okay, one thing to remember here is all of these four deal with orifice plates only. The second one deals with the specifications, which is the most important out of the four. The third one basically deals with application of 1, 2, and 4, these three chapters. And finally, the fourth one deals with what was the background, how was this developed, etc. So let us look into this chapter 2, which is specifications. Similar to your ISO standard, APA MPMS 14.3.2 also has a straight run table, and it is very similar to ISO 5167. But if you comparatively, if you see, this is more strict than ISO 5167. Why? Because if you see the word MPMS here, it stands for Manual for Petroleum Measurement Standards. So because the petroleum products are more costly, hazardous, etc., the more stricter ways are used. So more straight run requirements, etc., are defined here. But why do I personally love this and I would recommend you to read this standard is because if you see here, for example, I've made a video saying that when is the beta ratio between zero point 0.3 to zero point 0.6, etc. So if you see here in this chart, basically this chart is taken from API MPMS standard. The x-axis first you will have is beta ratio, and on the y-axis you're going to have the percentage uncertainty. Now if you see at very extreme lengths, which is zero point 0.1 or zero point 0.7 of beta ratio, if you see the uncertainty, it is too high. And if you see here, if we keep the beta ratio as zero point 0.1, the uncertainty could go up till 0.6, 60%. But if you see in the middle range between zero point 0.3 to zero point 0.6, here the uncertainty is far less. If you see the graph is going down. So we usually, that is why I recommend to keep the beta ratio between a middle range. So such insightful information is available in these API MPMS standards. Now, we have learned for Orifice plate these two amazing standards, which were ISO 5167 and API MPMS 14.3. There is another amazing standard which is ASME MFC 8M. But you would say, oh my god, there are already two amazing standards. Why do you need this one? This basically is the connection between the Orifice primary element to the transmitter. How is this area been taken care? Now, the engineering here is also very important. Let us try to take some examples for it. Now, imagine here in these two examples, the valves should not clash with each other. So what happens here is, for the first case, if you see, the piping offset is done. Both the valves are at the same elevation, but piping is trying to offset it so they don't clash. But if you see at the below side, the piping is same, but the valves are put at a different elevation so that they don't clash. There are various ways by, having a degree to it, etc. But all of these ways are covered in this standard. Similar to that, how should the transmitter be installed? So for gas service, it should be above the tapping. There should be certain slope towards the pipe. So because of gravity, if there is any liquid, it will fall back into the thing. So all of these amazing things are covered in these standard. And this MFC stands for measurement of fluid in closed conduit. Now let's look at the next one, which is fabrication. Now in Orifice plate, you might have the side view, certain things you might have seen. It is called as bevel. Now what is this bevel and how do you know what should be the angle for such a bevel? So for this case, we are having a PIP standard. I found this standard to be very amazing and I would highly recommend. This is a small snapshot of one case where if you see here, they've shown the bevels. Here they have shown is how should be the sample lettering done, what things should be written, basically what should be the dimensions. The dimensions are given in the below table. This is just to understand as to how the standard is and how you can give it to even a manufacturer so that you are very confident that everything is manufactured as per standard guidelines. Now finally, this amazing standard has also for flanges. Imagine this is your hypothetically your integral orifice. So this is all given by vendor, and basically these two flanges are where you need to fit your integral orifice. Now these are normal flanges, right? So for this cases, if you will actually see, the standard that we will be using is just ASME B 16.5, which is the normal standard for integral orifice. But if you see, special standard is made for orifice flanges because holes are drilled into them. So they'll directly start with maybe example 300 rating. And if you see, the other thing is they'll have jack screw in them so that you can remove the orifice plate, etc. So for such special cases, you will be having ASME B 16.36, which will be the standard used for orifice flanges. Now, if you tell me with this understanding for restriction orifice, what would you be using? Will you be using ASME B 16.5 or 16.36? The answer is 16.5 because there are no holes drilled in the flanges. So you can use for restriction orifice ASME B 16.5. Similarly, for pipe tappings, where the tappings will be taken from pipe for very high line size orifice, you don't need any special standard for flanges. So you can go for ASME B 16.5. Now, with so many standards coming into place, let us try to have a quick conclusion of all of them. The first one being is ISO 5167. The second standard is API MPMS 14.3. Both of them are similar, but API is having more stricter conditions. The third one being is ASME MFC 8M. This is specially used when you are having the connection between the tapping and your orifice transmitter. Finally, this fourth one is PIP standard, which is the fabrication standard. And finally, a special flange standard for orifice flange, which is ASME B 16.36. You can take a snap of it and you can remember these standards. There are even more standards, but these are one of the most used standards, and hence we have listed these five here. Finally, in for Orifice flow meters, if you want to learn about why is the beta ratio between zero point 0.3 to zero point 0.6, or how do you select the tappings for various things like integral orifice, flange tappings, etc., or why is there static limit and transporter, this playlist here is going to be very helpful to you. It covers all of these amazing things of Orifice flow meters. Thank you, and please let me know what other videos you want to see in the comment section, and we'll try to come and bring them together in next Saturday. Thank you and have a great day ahead.